Now that we've identified what an acid looks like and what a base looks like, let's look at what happens when they react together, which is a very common type of reaction called a neutralization reaction. When you think of neutralization, you may envision two armies neutralizing each other with identical forces. Okay, so really no one wins. Now, we said before that acids and bases tend to be very strong substances, but when they react together, they kind of zap each other of their strength and power. So we'll see that here in our example. So I'm going to use a little bit of red and blue here to indicate acids and bases. Traditionally, acids are indicated with a red color and bases with a blue color. That's easy to remember. So let's just take a simple neutralization reaction. We'll start with an acid. So I'll put an H there in red to indicate the acid. And let's just take a very common one, hydrochloric acid. And let's assume it's already dissolved in water, which it usually is when it reacts. And let's take one of our bases that we saw before. And in this case, I'll use the calcium hydroxide. Okay, so I'm going to use blue to indicate really the true base part of this substance. Just like here, the hydrogen is the acid part that gives the hydrochloric acid its acidic nature. Okay, so we see a reaction between two substances here. And again, the base would also be dissolved in water. And when they react together, what's going to happen is they're going to undergo a double replacement reaction, which I explain to my students often is really just ionic square dancing. Okay? What we can do is take these ions, and let's look at the four square dancers here. Just like in square dancing, you kind of swing your partner and you may end up dancing with someone else for a few minutes. That's what's going to happen here. So right now, the hydrogen and the chloride are dancing together, and their charges would be +1 and -1. And over here, to begin with, the calcium and the hydroxide are dancing together. The calcium from your periodic table has a +2 charge, and the hydroxide has a -1 charge. We do have two of them, so it would be a total of -2 to make this add up to 0. And all we're going to do is have them swap ionic partners here. So let's look at what we first get. Let's just go in order. The hydrogen from the acid with its positive charge would only be attracted to which of these two from the base, the positive or the negative? Well, we know in nature that ions of opposite charge attract. So the positive hydrogen ion is going to be attracted to the negative hydroxide ion, and you can probably see what we're going to make. When H and OH come together, that's just another way of drawing or writing out the formula for water. So water is one of the products of an acid-base neutralization reaction. What's the other product going to be? Let's put just a little L here. Since water isn't really dissolved in itself, we can just call it a liquid. It's one of the true liquids. The other product is going to be the other two partners coming together to dance. So that would be calcium with its +2 charge. Remember, positive always comes first. Calcium with its +2 charge, and the chloride with its -1 charge. So the second product would be, and sometimes it's good to do this scratch work down below, calcium with a +2, chloride with a -1. Well, it looks like I'm going to need, for the formula here, 2 chlorides to get the charges to add up to 0. And that's what we get. Calcium, chloride. And it is a salt. It's an ionic compound, so it will be dissolved in water. Okay, let me just move this over here a little bit. Okay. The last thing we want to do with an acid-base neutralization reaction is make sure, let me clean this up a little bit, make sure that we're balanced. Okay. So let's take a look at the ions in play. The hydrogen showed up over here as this hydrogen on the product side. So they were 1 and 1 each. Now the chloride, there's 1 here, but on the product side, we needed 2 for charge purposes. So what we need to do on this side is actually get the chlorides to balance by putting a 2 out in front here. That'll make 2 chlorides for us on this side, matching the 2 chlorides on this side. Now what that did, of course, you can probably tell, is that increased the number of hydrogens to 2. Okay, so just keep that in mind. We're talking about this hydrogen here. Now the calcium, there's 1 on this side, and there's 1 on this side, so the calciums are balanced. And then here's the neat thing about balancing acid-base reactions. if you get your products written correctly, and the key is to get that second product written correctly and always write water as HOH, watch what happens here. We now have 2 hydrogens here, and we now have 2 hydroxides here. So with 2 hydrogens, 2 H's, and 2 OH's, how many waters can we make? You guessed it, 2. Okay, and the rest of these coefficients can just be left to 1 as such. Okay? Let's leave that on the board, and let's do another acid-base reaction. Let's take this substance here. Let's take aluminum hydroxide. That would be a 3. And that would also be aqueous. And let's react it with sulfuric acid, okay, battery acid. And let's see what happens here. Again, first thing we want to do is identify the 4, call them square dancers, I guess. So first we have the aluminum, we have the hydroxide, we have the hydrogen again, and in this case we have the sulfate ion. Okay, so those are the 4 dancers. Charge-wise, let's go ahead and remind ourselves what the charges are, and use your periodic table if you need to refer to it. The charge on the aluminum is +3. It's out in front, so it has to have a positive charge. The hydroxide, just in the same as the last reaction, has a -1 charge. There are 3 of them, okay, to add up to a -3 to neutralize the charge here. On the acid here, the sulfuric acid, we have 2 hydrogens, but they each have a +1 charge. And the sulfate, if you look that up, has a -2 charge. The sulfate is this SO4 ion, just a big chunkier ion. Okay? So we've got some different charges here, and we need to pair these up to get our products. So let's do it in a different order this time. Let's take the aluminum, the first element here. Now again, remember what this is. This substance, aluminum hydroxide, this is going to be the base. All I've done is switch the order up. It doesn't matter what order we go in. Okay, so in this case, in the first example, I had acid, then base. Here I'm showing you base first, then acid. Okay, but it doesn't make any difference. So let's go ahead and pair up the products here for the salt first. It would be aluminum and sulfate. And the charges, I'm going to again do this kind of as scratch work down below. Aluminum and sulfate trying to come together to make a compound. Their charges, +3 and -2, don't add up to 0 and won't add up to 0 until they both get up to a value of 6. So what we're going to need here is actually 2 aluminums, each with a +3 charge, and a total of 3 sulfate ions, each with their -2 charge, to give us a product that looks like this. Al2 parentheses to hold your polyatomic ions. And how many did we need? We needed 3 of them. Okay? And again, don't worry about the balancing until we're all done with the products. We'll go back and fix this for the balancing here in a sec. Okay, let's get the second product. I should have left that. The second product is going to be the other 2 square dancers. And remember, positive comes first, so that would be the hydrogen and the hydroxide. Well, you saw in the first reaction, we just make water from hydrogen and hydroxide. We can put a liquid there, and this would also be aqueous. And there it is. Okay, completely neutralized. What was once a very powerful acid in both cases and a very powerful base has been neutralized to simply water and salt. Water and salt, which in a physiological sense in our bodies we can get rid of or retain as needed. Okay, so they neutralize each other and kind of take each other's power away. And quickly, let's balance this last reaction. Let's see. Let's do the metal first. So we've got 1 aluminum on this side, 2 aluminums on this side. It looks for the time being like we're going to need to put a 2 out in front of this aluminum to make 2 aluminums, and they're balanced. And let's just for the time being keep this a 1. What can we do next? The sulfates. Let's leave H and OH till the end. Sulfates, there is only 1 on this side, but we've got a bundle of 3 on this side. So we need to make some more sulfate on this side. If we put a 3 out in front there, that makes 3 sulfates for us to balance with the number of sulfates we see on the product side. And now again, when we balance the remaining 2 ions, the hydrogen and the hydroxide, look at what happens. We now have 3 times 2, or 6 hydrogens here, and we now have 2 times 3 hydroxides, 6 hydroxides and 6 hydrogens, so we can make a total of 6 waters on the product side. Okay? So double replacement, paying attention to your charges, and remembering that you always are going to make, in an acid-base neutralization reaction, water, and don't ever change the formula for water. Water is always HOH, or more commonly H2O. I think it's easier to see in this form. And you're also going to make a salt. Okay? And next we'll talk about weak neutralization reactions, or weak acid-base reactions that we see more commonly in our physiological environments.